this is lecture 10C, and in this lecture we'll give an example using the equations for a circle for the arc length and surface area for parametric equations. So we're going to look again at a circle of radius r. Of course, we like using this particular equation because it has a closed form solution. We're going to need those first derivatives, so we're going to go ahead and take them. The derivative of x with respect to time is minus r sine t, and derivative of y with respect to time is r times the cosine of t. Right. If you remember, the arc length function was the integral from t1 to t of the square root of the time derivative of x squared plus the time derivative of y squared. So we take these forms right here, substitute them in, and we can work through this equation. We'll have r squared sine squared ta plus r squared cosine squared ta. If we take the factor out the r's, which I did right here, you end up with the square root of sine squared plus cosine squared. But sine squared plus cosine squared is 1 by the Pythagorean theorem, so that that just becomes 1. Of course, square root of 1 is 1, and all we have is the integral from, we're going to go from 0 to t. We're going to start the circle at time t0. So we're integrating from 0 to t of d ta, and we end up with rt, which is the expression for the arc length around a circle. Because if you go all the way around a circle, it's 2 pi, and you end up with the circumference. So the arc length for the entire circle, as expected, is 2 pi r. So now let's apply those equations again to the circle to find the area enclosed by the circle. Right? So we're tracing this out in time. All right, so that's why we integrate with respect to time. So the area, we're going to go from 0 to 2 pi because that's the time it's taken to get all the way around the circle. 0 to 2 pi, we're integrating with respect to t. And the integrand is y of t times the first derivative of x. So y is r sine t, the first derivative of x is minus r cosine t. We end up with an r squared, which we can factor out the negative sign. Negative sign also, we're integrating from 0 to 2 pi of sine squared t dt. To evaluate this integral, we can use the formula for sine squared as 1/2 1 minus cosine 2t, the double angle formula. An evaluation gives us the area is pi r squared, and again that was expected result. It's nice when things work out the way we think they're going to work out. And now let's look at the surface area. If we took that upper half of the circle, so in other words, we're letting t go from 0 to pi, and out of that we create a figure of revolution. That figure of revolution, of course, will be a sphere, and we want the surface area of the sphere. So we integrate from 0 to pi of dt, and we multiply, and the integrand is 2 pi times y of t times the square root. Remember, this part here is the arc length differential. So the square root of dx by dt squared plus dy by dt squared. So if we worked this out, we would have r squared sine squared t plus r squared cosine squared t, and again we end up with just an r for all of, whoops, I didn't get the pin, for all of this, and the equation becomes 2 pi r squared because y is r times the sine of t, and all we're left with to integrate is 0 to pi of sine t dt. Evaluation gives us 4 pi r squared, which is the surface area for a sphere. Again, this was a nice example because it has a closed form solutions. For parametric equations or any equations in which you do not have a closed form solution, you can set them up. You set up the arc length, you set up the surface area according to the formula that has been developed, and then you use numerical integration to evaluate it.